let's take a look at calculating work in physics. Really the focus here is actually going to be on the math, but we'll go over a little bit of physics to apply the math. So our formula that we're going to be looking at is work equals force times distance. Okay, and so let's say we have a some kind of a solid object. We'll make it a little cube here. Okay, so that's cube. So we have this little cube, and let's just say that this cube weighs 3 pounds. 3 pounds, and let's say that make this the shadow of the. This is the shadow of the cube representing the ground. Let's say we're going to take this cube starting on the ground here and raise it up 20 feet. So how much work was done? Well, we're going to take work equals force times distance. Our force is 3 pounds. And our distance is 20 feet. So our work is 60 foot-pounds. 60 foot-pounds. Okay, and so for the little example here with this cube that weighs 3 pounds, whatever it's made of, maybe wood, and we're going to lift it 20 feet. So during this process, we're assuming that it's just the same. I mean, I guess if it was starting from 0, maybe it'd be better if it was actually starting from not from 0 movement, but we're only considering that we're taking a constant force of 3 pounds and we're applying that force over a distance, and during the whole duration of the distance, the whole duration of traveling this distance, the force is the same. The force is always 3 pounds as we push this cube 20 feet. So then we can use this formula as was just given, and we can get 60 pounds per foot. But let's section this off. Let's take another example. Let's say we have this really tall building, and this will be straight. Say we have this building here. The height really doesn't matter, but it has to be longer than 20 feet because that's how long I'm going to make a rope hang over the edge. It's going to be hanging down 20 feet, so the building's got to be taller than 20 feet. So we have this little tiny man hanging out on the roof, and he has a rope in his hands, and the rope is hanging down over the building. Okay, and for illustrative purposes, I like to imagine there's a little pulley here, because we're only going to be paying attention, and actually that the pulley is at the very edge of the building. I should have made it hanging out over the side. Anyway, so there's this pulley there, and because we're only going to be paying attention to the pulling of the rope over the pulley. So from the pulley down to the end of the rope, that's what we're going to be paying attention to. And let's say that that distance is 20 feet. And let's say that the type of rope that we're using, it is 3 pounds per foot. What that means is every foot length of this rope weighs 3 pounds. So it's a really heavy rope. And maybe it's steel cable or something. Anyway, 3 pounds per foot, 20 feet. But now in this situation, we have the same numbers as last time with the cube, but the solution to this will not be 60. It will not be 60 foot-pounds. The reason is 60 foot-pounds is only the amount of work that it takes to pull the very end of the rope up to the pulley. But we're not only pulling the very end of the rope up to the pulley, we're pulling many sections of the rope. So I make a little tick mark down here. To pull that little piece up to the pulley is 60 foot-pounds. But when I pull from the middle here, I also have to pull this little section of the rope. And that is not a distance of 20 feet. It's still 3 pounds per foot, but the distance is not 20 feet. If this x were halfway, it would be 10 feet. Okay? Put another x up here where I have to pull a distance that's 5 feet, and x up here where I pull a distance that's 2 feet, x up here where I pull a distance 1 feet. I had to pull the x down here for the distance that was 18 feet. And so for every individual distance, for every little piece of the rope, it has a different distance, and we need to take into account that distance as we pull this rope. So when we first start to pull, our distance is going to be here at the pulley where we're beginning for our purposes right now, beginning our calculation. So when we pull over that pulley, the starting distance is 0, because when we very first start to pull, it's 0, and as we pull, all of a sudden now it's 1 inch, it's 2 inches, it's 3, it's 4, now it's a foot, now it's 2 feet, now it's 3 feet, and as we're pulling up this rope, the distance that the rope had to travel to get to the pulley is growing. So as we get all the way to the end of the rope, we're going to have a distance of 20 feet. So in this particular problem, we're going to have 0 at the pulley and 20 all the way down at the end of the rope. The type of, yeah, we'll just, so from 0 to 20, now the formula that we're going to use is work equals integral from a to b of f of x dx. So f of x, this represents our force, our formula for our force. Okay, and the force, it has an x because the force is changing, as I already illustrated. The work required to carry the very end of the rope up to the pulley will be 60 foot-pounds. It will be 3 pounds per foot times, is that right? Times 20 feet. Anyway, it will be big. So it will be a bigger number. And as we get to the, halfway, it will be a smaller number. As we get up to almost to the pulley, it will be a very small number. But the distance that we're pulling changes the amount of force that is used to pull that little section of rope. Then I didn't leave myself enough room here. I'll do it down here. The A, the B, and the dx are all representing the summation of the work. So So during this process, we could calculate work for the individual sections of rope and add up the values that we find for work, add all of those up to get our total work, and that would be, well, it would be an approximation, and the smaller we make our sections of rope that we calculate for, the closer our approximation will be to the exact answer. So if we were to just calculate the bottom half of the rope and the top half of the rope, our approximation is going to be really far off, actually. But if we were to break the entire rope up into 1 foot sections and calculate for each 1 foot section how much work was done to pull that 1 foot section up, then our approximation will be closer. But if we break it up into inches instead, if we break the rope up into sections of inches and we calculate how much work is done for each inch and then add up all of the work that we calculated, that will be an even closer approximation. Okay, and then you just kind of keep doing this until your pieces of rope get infinitesimally small, and then that's basically what an integral is. So that's what why we use an integral here to calculate work on this rope. And so to plug in the numbers, it's going to be work equals the integral from 0, that's our starting point, where we have not yet done any work, to 20, which is the end point where we have done our maximum amount of work, of our formula for force is 3 pounds per foot times x feet. Because what we're plugging in for x here each time is every possible number from 0 to 20, basically. And then dx. So now to solve this integral, that's how you write it. To solve it, you use the power rule. So work equals 3x squared over 2. And then you're solving again from 0 to 20. I like the bracket on the left-hand side as well. Then when you solve this integral, you're going to basically plug in 20 into the thing we have written out there, then subtract plugging in 0. But you can see when we plug in 0, we're going to get 0 times 3, which is 0, divided by 2, which is 0. So we're going to find some number and subtract away 0. So subtracting away 0, we can ignore that. So we're just going to have work equals 3 times 20 squared over 2. 20 squared is 400, which you could say 20 times 20, we get 0 and 0 for that row. Second row, we start with a 0, then we say 2 times 0 is 0, 2 times 4 is 4. We add them together, get 400. Okay, so we're going to have 3 times 400 over 2. It's going to be easier if we take 400 and divide it by 2 first, so let's do that. Work equals 3 times 200, and we get work equals 600. And once again, same units as in our previous example, it's going to be foot-pounds. So 600 is nowhere near 60. So that's what we get. 600 foot-pounds is the amount of work required to pull this entire 20-foot section of rope up over this pulley to the top of this building, whereas 60 foot-pounds was the amount of work required to raise our 3-pound block 20 feet off the ground. The difference between constant force and variable force. Now just another little fun math thing, another way to think about what we just did. So integrals also represent finding the area under a curve. So as we look at this, I kind of, I solved this and I said, well, what curve did we just find the area under? What would our curve be? So we have our little Cartesian plane here, little arrows. Okay, so if we start at 0, which is the x value that we started at, so this is our x-axis, like what is standard, this is our y-axis. So we're going to move along our x-axis because that's how we actually set up our integral. The integral from a to b of f of x dx, typically that would be mean that we're traveling along the x-axis. And we're traveling from 0 to 20. Get it right here. This is not going to be the scale, I don't think, because of the way I set it up. We're traveling from 0 to 20. And we know that the last position of the rope, so from 0 to 20 represents distance. The x value represents distance on this Cartesian plane. The y value represents work, because that's what we are. Or would it be force? No, actually it's force. Yeah, so the y value represents force. Now the force for the last little section of the rope is the full length of the rope, which is 20 pounds per foot times, 3 pounds per foot. 3 pounds per foot. Okay, so the force of just of the full length of the rope. The force that we're going to be using for the full length of the rope, which would basically be the weight of the full length of the rope, is 20 feet times 3 pounds per foot. The feet will cancel, and we're going to be left with 60 pounds. So our final point on the just our final point total will be the point with an x value of 20 and a y value of 60, because the full force, the max force that we're doing is 60, and every other point will be smaller than that. And the amount of force done for the very beginning of the rope is 0 because we haven't started moving yet. And as we slowly start to pull those inches over that pulley, we slowly end up with more and more force that we have to enact. Okay. Now you can see that we've made a right triangle. Yeah, I can't fully prove or explain why that's a right triangle in this instance. Just go with me for now that it is a right triangle and not some other shape. That the curve's not some other curve. So we have our x value, our length of the base of our triangle is 20. Our length of our height of the triangle is 60. Which actually we can keep the units and this still works. So this is 60 pounds because it's force, and this is 20 feet because it's distance. Now when we calculate for the area, of this triangle, we have area equals 1/2 base times height. Area equals 1/2 base times height because it's a triangle. So, which equals 1/2. Our base is 20 feet. And our height is, our height of the triangle, not height in reality, is 60 pounds. I thought 60 pounds, that can't be a height, it's pounds. But it's the height of the triangle, and the value is 60 pounds. Now, when we multiply this out, 1/2 times 20 is 10, 10 times 60 is 600. So we get 600 foot-pounds. So, in fact, our area does equal our area under our curve does equal our work calculated. So our integral did, in essence, find us the area under our curve. There you go.